All right, welcome back to CE 528. We are just picking up the discussion from cost modeling. And I am aware that I have this lamp right here that puts a pretty bright light on me on one side of my face, but we'll live with that. So we are trying to wrap up the discussion on cost modeling. And the idea of cost modeling and the average cost and all that is trying to look for how do we model cost, and there are different ways of doing that. If you are the contractor, for example, for a project, you almost need an engineering cost model. You need to have very good knowledge. We have very, very good knowledge of the project, the exact details, what you're going to build and all that. But sometimes for planning purposes, you can get away with doing what we call the statistical cost models that don't have to be that exact, and they could be somewhat approximate. You could base your estimates based on historical data, and that sort of things that we were talking about. And I gave you an example of a fuel use case, and that example is not something that I'm going to test you on or anything like that, but that was just to give you an idea about you had to estimate the tractive force at different forces, how much fuel you're going to use, and so on and so forth. So that was an example of the engineering cost model. But if you want to do the same thing using the statistical cost model, you can apply much more simplistic approaches. And let me go ahead and share that with you. So some of the models that we were looking at, so this was the sort of the engineering cost model that I showed you in the last class. Just want to give you the example, like the level of details that you might require. But if you're looking for some statistical cost models, you can just look for, some data from certain semi-trucks that were running, and they were running at different velocities. And then you just estimate how much fuel they were using per travel 1,000 miles. So you can see the speed of 45 miles per hour basically provides the least amount of cost, and so on and so forth. And this is for the automobile, this is for the truck. For the truck, the gallons per mile is a little bit higher, obviously. You can see the scale is different. And you can see different grades. Steep grades means more fuel consumption and so forth. And then you know that at different velocities, you have different fuel consumptions as well. And then you could do the same thing for oil consumption. So fuel, and this is the engine oil consumption. You could do the same thing. And again, if you are at how many quarts per 1,000 miles, if you're talking about low velocities, that will require more fuel, more oil consumption. But if you are able to maintain a high velocity, then there is less fuel consumption for the fuels and the trucks. And you can combine this information to come up with the cost of fuel and cost of engine oil. You can combine that information to then come up with basically an addition of those two sub-cost models. So there is one sub-cost model or cost sub-model for the fuel consumption. There is one cost sub-model for the oil consumption, and you can combine the two to come up with what you might call the total cost of operation. And you can then try to minimize that total cost of operation. And this data, by the way, comes from an old NCHRP project, National Cooperative Highway Research Program Project 712 from a long time ago. But some of those things are still valid. Those basic ideas are still valid, how you can combine those sub-models. Same, the tire consumption, obviously. And then this is another sub-model. And in this sub-model, you could see that at lower capacity, lower velocity, lower speeds, the tire doesn't, you don't do as much tire damage. But as you increase it, the tire damage goes up for both, for automobiles as well as for the trucks. And then truck annual depreciation, the depreciation value is lower, percentage of vehicle value lost per 1,000 miles. Obviously, if you're driving freeway miles at higher speed, you don't get as much depreciation because your engine doesn't have to work as much if you're driving on a higher speed. So what you're seeing here is this 4 examples of 4 statistical cost submodels. And typically we combine these submodels to come up with the overall cost model. Okay? So, and then you could see that these are all pulling in different directions. Some cost submodels indicate that the cost will be, that submodel cost would be lower at lower speed and higher at higher speed. And some have the opposite thing going on, where you have higher speed means more cost. And when you combine the two, you combine all 4 of them, 4 submodels that I showed you. You can combine vehicle depreciation, tire consumption, oil consumption, fuel consumption submodels to come up with an total optimization of speed so that you minimize your total operation cost. And we're going to do a lab based on that. Our next lab is in fact going to be based on this. So we'll talk about that, okay? And then let's talk about construction cost. So in way cost, the cost reflects geometric design standards and the environment to be crossed. And that'll be topography, soils, hydrology, prior development. That'll determine how much cost you will require to, how much cost it will take to actually acquire the land if there is that needed. You know, and you might need engineering cost models here when you're looking at the construction cost, site preparation, major structures and minor structures, earthwork, excavation, hauling and disposal, placement of the running surface, final way details, fences, traffic control, electrification, and then terminal stations, intersection, all those things. Cost models are typically just accounting processes based on estimated quantities and unit cost. But the timing of these large lump costs can substantially affect the project's benefit cost comparison. So if you have to budget for that cost right at year 0 versus if you have to cost at year 2 or year 3, and these construction projects last very long as well. So depending upon exactly where that cost comes in, you would have to account for them in their proper timeline. And we all know that the dollar spent today is more valuable than the dollar spent 1 or 2 years from now. So that accounting might also affect the benefit cost considerations. And then there might be some ongoing way maintenance costs that will be minor surface repairs, vegetation control, painting, clearing debris, and then traffic control, enforcement, other operational requirements. And then there might be major maintenance and rehabilitation that you might have to do periodically, but less frequently than annually. So every maybe 5 years, you might have to reseal or repave your roads and whatnot. Maybe you have to apply some sealant onto the pavement. So there could be some cost of that. And that might be dictated by your maintenance policy. So here, I want everybody to pay attention and just kind of point out that your next lab that I just mentioned is in fact going to be based on what is the optimum time to repair a certain road. And I'll give you some cost submodels built into an Excel sheet. And then I'm going to just ask you to come up with what's the best time to be maintaining that particular road. And then way cost component estimation, each component requires a suitable cost estimation technique. It generally involves use of simple engineering models or statistical model to estimate the quantities, and then you combine them with the unit costs. So here is an engineering cost model for site clearing. So how much would it cost? And then so ACG is the average area of the site clearing and grubbing per unit length of road in meters squares per kilometer. And then GRF is the ground rise plus fall in meters per kilometer. And then you could see all these different, this is sort of what it looks like, what the terrain looks like. And then this is the one, the broken line here represents the road profile and the actual ground profile. And then RW is the roadway width, and then W plus the shoulder width. So this is sort of the right of way width. And then W is the width of carriageway. WS is the width of one shoulder. So you have to have shoulder on both sides. So you kind of account for that. And then the ground rise plus fall would be R1 plus R2 plus R3 plus F1 plus F2. So you can combine the two and divide that by the length. So you can figure out what's going to be your total net GRF. And then based on that, you can come up with, so this is all based on what we call the highway design and maintenance standard model, or highway design model. And we're going to use a poor man's version of this model in our next lab. Okay, so we'll use like a simplistic model. And then this is some old calculations, but some of these numbers might have changed in terms of the unit cost, but the way we do excavation and stuff like that, the unit costs have changed, but the area estimation is still done pretty much the similar ways that we are going to be using there. And again, the precise nature of these formulas is not as important. I'm not teaching you highway design or anything like that, but I'm just trying to show you how the process actually works in terms of an engineering model for site clearing. You need so much detail about the ground profile and the roadway profile and all of that, so that you can make an accurate estimation of the cost. And that's why this is an engineering model and not a statistical model. And what might a statistical model look like, you might ask? So you might do simple calculation based on your old projects and so forth. So you just say, okay, as the roadway width increases, obviously your cost, predicted earthquake volume will increase. Okay. And how much would it increase? If G is equal to 0, G is 20, and Z is 40. And then where rise and fall of the ground, this is RF is the rise and fall of the roadway. If GRF is 100 and RF is 60, this is what the cost will look like. And the cost will look like RF is 0 and GRF is 40. The cost will look like these. And you could see that the G value, the rise plus fall differential, is the same. But the cost is still different if you're dealing with a higher elevation. Okay, so you can see that the net value, the rise and fall differential, is the exact same. Right? The rise and fall differential is the exact same. The G value is exact same. And rise plus fall of the roadway. So even if the net value is the same, whether you're talking about 160 or 40 and 0, there is some difference between the costs, or the net earthwork really. And that's what's reflected in these two curves. And if it's 0, then you're dealing with basically no earthwork. And then if it's 100, then this is how it goes up. And then you're given. So what you're estimating is the predicted earthwork volume here. And then this is based on historical projects, and you're just graphing these out. So instead of this detailed level of the exact nature of the project, you're just kind of making work with, okay, what's the net value? Let's get that, and then predict it. And based on that prediction, you can figure out, okay, how much budget to allocate for planning purposes. Okay, so there are some major resources where you can get most major agencies that do construction and maintenance maintain databases of unit costs and typical quantity estimate for projects of various types. And then here are some links that I provide you. You can look those up, and engineering news record and RS means. These are some published data. The published data are appropriate for typical components, but if you have unique major structures, you might need some customized analysis. If you have some unique structure that you're dealing with, then you might have to, do more engineering cost model type estimate. You may not be able to rely on the published resources. So I hope you got some sense of how costs relate with pricing under different structures, and then how do we actually estimate costs of something. And with this, that lecture, I'm going to conclude this lecture unless there are any questions. Obviously, we're not going to get off for the class. We still have, we're going to start the new lecture, but I'll wrap up the discussion around cost structures and so forth. Are there any questions? Okay, I'm going to go ahead and stop recording.